the language of the universe.
But I don't understand it.
Hello, everybody. Welcome back to the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we welcome you to episode number 53, where today we have special guest Dr. Trefor Bazett on the podcast here with us. Dr. Bazett is an assistant teaching professor at the University of Victoria in British Columbia, and he got his PhD at the University of Toronto. So big proud moment for us here at the podcast. So
happy to represent U of T for sure.
Absolutely. So Trefor, maybe you want to talk a little bit about your assistant teaching professor job at University of Victoria, just like a brief introduction on what you do there. And yeah, let's hear it.
Absolutely. Well, thank you both for having me on. I've really enjoyed learning about your podcast and watching some of the episodes. I think it's great. I think it's awesome. So I'm really excited to be here. And I love that you guys are from U of T here. That just is a fun connection.
Mm-hmm. Mm-hmm,
right. So
sure.
I'm an assistant teaching professor at the University of Victoria, as you mentioned. And so from a teaching perspective, what I mainly am doing these days is I'm sort of going the second year calculus sequence, multivariable calculus, vector calculus, differential equations. Anyone that goes through those courses are probably going to get me at the University of Victoria. And then I do some fun stuff in third year, like math modeling and that kind of stuff.
Mm-hmm.
And so I'm an assistant teaching professor. That means most of my focus is on teaching. So the kind of scholarship that I do is all tangential to teaching as well, and trying to help people learn and help us develop the best courses that we can. And then I have this weird side gig, I suppose, on YouTube, where I just post my math videos on YouTube as well. So I don't know. I guess I'm a professor / YouTuber these days, which is a weird thing to be.
And the videos that you make, are they tailored for like the students that you teach, and then you also just happen to post them on YouTube, or are they for YouTube?
That was originally the plan.
Okay.
Yeah, for bizarrely, several years ago, before the pandemic, I was tasked with teaching this online course for discrete math for information technology students of all things.
Oh, cool.
And I had 20 students in my class. It had to be online because it was they all had jobs, and so they were doing it remotely. And so I just posted some videos on YouTube, and I really just didn't think anything of it. It was just that's where you were going to go and put them, because where else? And then those videos, they just sort of really took off. And so now I've consistently, as I've gone through a series of courses, it was first like, I'll do a flipped classroom. And the videos from the flipped classroom will go up online. And then of course we had a pandemic. So I've been posting the videos from the pandemic. I occasionally post a video that's just cool math.
Yeah.
I just want to do something fun for myself and for the people who follow. And hopefully after the pandemic, I'll stop posting videos for my courses and just do that. But, that's a little ways away.
I mean, to be honest, like those videos, amazing. Like those videos have helped us so much in our calculus course in our second year here. I'm so happy. in our proofs related course, because I don't think a lot of mathematics like YouTubers especially get also into the proofs and the reasonings behind a lot of these theories. Like they'll just present the theory, talk a little bit about it, but I don't know, like the way that you talk and you have your visual thing right on the side. So if any one of our listeners hasn't seen Dr. Bazett's YouTube channel, make sure to check it out. Really helps a lot. And plus, like our class, so Parker and I are in Mat 237, which is like our second year equivalent of multivariable calculus, where we deal with proofs and logic and all that good stuff. And a lot of our requirements before classes is to watch your videos. So they act like the department will basically tell us we'll have a bunch of like pre-class
I don't know if
essentials.
it's the department.
Sorry?
It's not the department. I think it's just like the teacher.
I guess
like
the teacher,
professor.
I guess in our section maybe I'm not too sure on how this is, but anyways, I mean the idea is that we're required to watch these before class, and that's what I'm trying to say. Like it truly helps not only for class especially, but just in general if you're trying to get into like understanding a little bit of math here and there. So I think it's super helpful. And before we get right into the podcast, we have our segment of news. So let's start up with the comment of the week. So on the most recent episode, we got Devin Hardy. So shout out Devin Hardy for saying, to be honest, a lot of these comments are amazing. It's just that we had to pick one. So here we are. We picked Devin Hardy, the first one that commented. So Devin says, I love your podcast. This is the only thing that can get me to study. So keep up the good work.
Thank you so much.
Devin. Thank you for those kind words, and we will keep it up. Thank you. So
yeah,
Parker,
if you want to get your comment shouted out, make sure to leave a comment either on YouTube or on Instagram at math.physics.podcast. In other news, we are currently at 6,277 followers on Spotify. So thank you so much to everybody that is following us and listening to the podcast. And you know what? If you're listening right now, make sure to follow us. Hit the subscribe button. You know what? That might be the thing to make our day today. Other than that,
I mean, as Dr. Bazett says, sorry for cutting you off.
Yeah.
Sorry for cutting you off. But because you were talking about the subscribers, I have to mention this. I love, Trevor, I love how you end your videos with we all love algorithms, so help the YouTube algorithm and give it a like. I just love that part because we're all mathematicians here. We love the algorithms. So we got to make it work. Sorry, Parker, I cut you off in the middle of the downloads.
Sure. I was just going to say, we're at 81,000 downloads, so very close to 100,000.
That's amazing.
So, tell your friends. Help the algorithm once again.
Yeah, help the algorithm.
And,
tell your friends, tell your parents.
I guess that's it for the news.
Tell everyone. Yeah. Okay. So let's get into it. Let's get into the podcast with the classic question. The question that we ask all of our guests on the podcast. The very first one. What got you into your field? Like, what made you interested in mathematics? Was there like was there a particular moment in your childhood? Was it a sequence, like a series of events that led up to it? What was it?
Yeah, that's a good question. Okay, I think I got two moments. Which do you want first? Do you want elementary school or do you want undergrad?
Let's have a chronological. So okay,
we'll go chronological. I really put a lot of stock in the elementary school answer because I was in this program when we were in elementary school, and basically 1 hour a week, a bunch of us got together and we just literally solved random logic math puzzles for a week.
Wow.
And it was so cool for an hour. It was such a cool thing. And I sort of don't like it in the sense that at the time it was referred to as a gifted program, which is a term that I really reject these days and I think is actually quite harmful. But that's what it was called regardless. But really what it just was just a bunch of people just going and just solving problems. And the teacher even tried to get us to be a bit more focused on, doing specific projects, but we just literally just wanted to solve random problems. And so what it meant was that for about 3 years, grades 5 to 7, there's this regular and very authentic time period where you could be doing actual mathematics, not mathematics in like some high level thing, but just trying to solve interesting problems using logic puzzles and all that kind of stuff. And I think that really cemented a love of mathematics, that you enjoyed the sort of problem solving aspect of it. Because often this can be kind of taken away from you when you're in those grades and you're having to do lots of rote memorization, lots of sort of algorithmic, procedural fluency type of things. So I thought it was really useful. It also had this sort of weird sense. Our school was similar to having this program, was really focused on the sort of national like math contests that would go on, like they called them like the Pythagoras or the Gauss or things. This would be something that would go in Canada.
Right.
Of course.
And our school was really focused on really teaching to those contests. So for everybody, regardless of what program's in, we would have a second hour on Fridays where you're just doing problems from those contests. And as you can imagine, the school in general, like a lot of people from the school just all did well. And so you had this sort of a sense of accomplishment as well. I mean, now I think of this mainly, which is it's a product of the upbringing that you have, that you would do well, but at the time it feels really good.
You're talking about Olympiads, right? When you're saying
Not the Math Olympiad.
so
No,
you're not talking about okay, because I
no,
was
they're not
thinking
even that. They're not even that good. I mean, I can tell you, I remember screwing up a question because I didn't know how many sides there were on a cube, and went backwards on this. It said 8 instead of 6. Otherwise, I would have done well. But so nothing crazy, because it's like grades 5, grade 6, grade 7 kind of age frame. And then after that, I really stagnated for a long time. So there was this sense that people had said, "You're good at math. Here's your evidence. You went to the school that trained you to do contests, that go off and do these contests." And I enjoyed math, but I was sort of kind of apathetic in high school, and so I had this sort of background liking, but wasn't really engaged in it. So then I went to university, and at university I initially started in computer science. And then I went to physics because I didn't like the computer science that much. And I really thought of myself as a physicist for pretty much all of my undergrad. All of my friends were in physics. I was in physics. But then I started taking the math courses you had to take. And I really, really, really enjoyed it. I think I started, where it first made a difference was taking a group theory course. And this was the first time I was introduced to like definition, theorem, proof style of mathematics. And I just really, really enjoyed it. And so I switched and tried to be a combined math and physics. And then I saw analysis, and you keep on having all these weird connections. Like you'd be in quantum mechanics, and everyone would be totally confused with what's going on in quantum mechanics. You're like, oh, this is just a projection in some infinite dimensional Hilbert space or whatever it would be, right? And you'd see those connections going back and forth. And that took me to the dark side of math. And so I went off to be a mathematician after that.
Wow.
That's my story.
Wow, that's truly an inspirational story.
Okay, yeah, I was gonna say, it's funny you say like the dark side of math, because as like a physics student, I'm not really orienting myself towards like the analysis part of math, and I think I'm gonna stick more to like just well, right now I'm doing like the proofs and calculus, but that doesn't really count. It just helps me grasp the theorems a little bit more. But I think I'm gonna stay more in like the practical side of math. And it's funny because I see on YouTube like, for example, Black Pen Red Pen, and he's like, this is adult calculus, where he does like analysis problems, and then the rest is just like like the easy calculus.
Yeah, I love his videos. They're the easy calculus, as you put it. No, they're great because they just get to play around. I mean, he really is good at just playing around with interesting calculus problems, and that's what that channel is just so good for.
True. I love how I think recently I think he posted like a quick Instagram snippet or something where he was talking about like the superscript on the left versus the right, where the left is the adult, where you're doing to the power of to the power of to the power of kind of situation. Mm-hmm. So I don't know. I do love how he plays around with it, but I think like the only thing that's daunting, or at least me personally, about like mathematics and continued study in mathematics, just math, not getting physics in here, is simply the fact that after a certain level, again, you can correct me if I'm wrong, this is just what I think, but after a certain level, it just gets incredibly abstract. Like, it gets so just vague. It's all in your head. Like, you can't actually make sense, or I guess you can, that's wrong phrasing, but like a lot of the times, like a lot of problems, especially when we're dealing with like 4 and 5 and 6 dimensions, like it's all just in your head. Like, you can't really put it on paper or even sometimes visualize it. So how do you overcome that barrier, or is that something that you enjoy, the fact that there is lack of visualization and it's all in your head?
Yeah, that's really interesting. It's interesting to hear how you frame it. Can I ask, have you guys taken linear algebra yet in your development?
Yeah.
So for anyone who's listening who hasn't done it, I mean, linear algebra is the study of linear transformations, and in one dimension, those are relatively simple, like y equals 2x plus 1, for example. But one of the things that we do is we try to generalize that to a general linear transformation between a larger number of dimensions. And so you're right to phrase it, there becomes an amount of abstraction that happens. But at the same time, when you work with these tools a lot, you start to see, you build an intuition in that domain. Like, for example, you'll learn how to do, I talked about projections already, we'll learn how to do projections just, for example, in 2 dimensions. And then you can ask a question, well, what does a projection look like in n dimensions onto some n-1 dimensional hyperplane or something crazy like this? And those sound really weird, but if you're grounding your intuition and your mental pictures and things that you do understand, I think it creates an avenue to be able to understand those concepts. And a lot of higher level math, when you're trying to wrestle with something that, you're right, might seem new and big and abstract and challenging, is that you want to think through it in terms of concrete toy examples that illustrate the key intuition. And then eventually you see the forest for all the trees that are sticking in front of you. But there is a lot of trees. I will acknowledge that.
Very many, very many.
When we do do projections from like an n dimension down to an n-1, you can kind of just think about it as if it was like 3 dimensions to 2 dimensions, even though it's not the exact same thing, but that's what's happening.
The idea is still there, but the thing is, especially like in our class, and I think this should be with all multivariable classes, is that they teach you from 3. Like everything starts with 3 dimensions because you can visualize that, right? And like if we're talking about projections for this example, it's 3 to 2. We're never really dealing with 4 dimensions to 3 because there's no way of visualizing what that image would look like. So I guess I do actually see your point, Parker, where like we are given an idea with 3 dimensions and then we can apply that same logic to n dimensions, right? But yeah. I guess this kind of brings up a question in my head where is there any particular like a theory or something, again, I'm not quite sure, that exists for 3 dimensions but is different when you start adding dimensions. Like when you start adding dimensions, like the theory changes depending on the number of dimensions or something like that. Like, is there something like that?
Yeah, absolutely. So it is worth noting that your general sense is true, that when you jump up from, let's say, 1 dimensions to 2 dimensions, things get a lot harder. So the classic multivariable example of this is the concept of a limit. So in 1 dimension, if you want to approach some point, you can come from the left and you can come from the right. There's only 2 options. So it's pretty easy to do. But as soon as you go to 2 dimensions, then you're stuck with the issue that you can approach it from any, like infinitely many directions, but you can also approach it from different paths that weave around. And there's this large part of multivariable calculus that you have to be really precise about. What do you mean by a limit? That, for example, the limit along 2 different paths that even end up being tangential can have different values. Like, it's kind of crazy. Okay, so that's going from 1 to 2. But then, well, what happens if you go from 2 to 3 or 2 to 700? A lot of the complexity is not that different. You might talk about the distance between 2 points. Previously might have been a square root of a sum of squares. You just have more in the sum than you did previously, and so forth. So a lot of the time, it's the case that after you've gone from 1 to 2, that's just as difficult as going from 1 to n. And different teachers sometimes, like you talked about how your teachers were really presenting stuff in 3 dimensions. I sometimes do that, but sometimes I'll just generalize right to n dimensions and just be there. That's not always the case, though. There are definitely times where there's weird things that occur in only specific types of dimensions. So, for example, you can ask about maps between spheres, and there's all sorts of interesting things that happen here where things only work in certain types of dimensions. I even remember in my thesis, there was this one weird thing where, for some reason, dimension 6 mattered. And then after that, it sort of stopped mattering for whatever weird reason of the details of it.
That's an interesting one.
And then somehow this sort of skeleton that only happened in 6 dimensions was all that was interesting. And then after that, yes, there were more dimensions, but they stopped being interesting. But you had to get sort of something specific to make that point precise.
Okay, so I guess continuing on in Trevor's life, we have you taking your PhD at the University of Toronto, right? So what was that experience like?
Oh, it was an experience.
It was an
So I mentioned how I came out of undergraduate with a physics and a math degree.
Yeah.
And because I had really started in physics and I say thought of myself as a physicist primarily, where you're taking math courses in service of the physics at the beginning, I was taking the types of math courses that were compatible with physics. So for example, I took an enormous number of differential equations courses. Every differential equations course the University of Victoria offered, basically, because you need a lot of differential equations when you're doing physics.
True.
But either way, at this point, I'd been sort of convinced that I wanted to go into mathematics and that I really enjoyed that part of it. And I didn't even want to go into applied mathematics. I didn't even want to go to mathematics tangential to physics. I wanted the purest mathematics I could find, which is a silly thing, but that's all right. So I went to the University of Toronto, and the way graduate studies work there is their master's is basically a one-year master's. You're doing coursework and a little project over the summer, and then getting the master's is relatively easy in comparison to a thesis 2-year based master's.
Of course.
And then you're also, as long as you do well at that, you go into the PhD program. And so the first little bit is really about laying all the foundations. So you need to, by the end of 2 years there, you want to have passed a series of comprehensive exams in the core topics of mathematics. You get a little bit of choice. So for example, for myself, I think it was real analysis, complex analysis, algebra, and topology. But I could have swapped one of those out and put in PDEs or something like this if I wanted to. But you can already tell, perhaps by my shift away, that I didn't take PDEs, even though I had a lot of differential equations experience in my undergrad. And so that was great. And then after that phase, you're already starting to think about like, what do you want to do for like a thesis, and who are you going to work with? And you're taking sort of fun specialist courses. And I really fell in love with topology and algebraic topology specifically. So topology as a field is kind of like geometry. It's the study of shapes. But where in geometry, you really care, geometry is sort of rigid. You care about like the angle between things. Like there's the theorems about angles and there's theorems about lengths. There's sort of rigidity to it. Whereas in topology, you ignore that sort of rigidity. And the standard joke is that a donut is topologically equivalent to a coffee cup with a single handle, because they're both sort of three-dimensional objects with a single hole. And if you can imagine them being made out of Play-Doh, one can transform into the other. Who knows, maybe we'll talk more about topology later. But the point being that this was this type of mathematics that I found to be really interesting. I even actually did in undergrad, a directed studies course in this. I don't even know how I found the field. I think maybe I was just looking on, maybe r/math or something silly back then. I don't even know, or Stack Exchange or something like this. But I got interested in that and I really enjoyed it. And so that was sort of the direction that I went. And so you work for a number of years and you try to do something original, and then that's your thesis. But I also think it's somewhat important for me to say that, so in this period, you do sort of a progression on the teaching side as well. So, to pay your way as graduate studies, like if you're going to go and become a graduate student, you're very likely to get some sort of stipend, and that you have to work for it. And some of the things you'd work is some sort of teaching, marking initially, and then leading tutorials, and then leading full classes, and so forth. And so for myself, I actually found that I didn't expect this, because I had no interest in teaching going in. But by the time it got to tutorials, I really enjoyed the teaching side of this, and was really excited to teach my first class, which was differential equations. And I just, I really loved the teaching side of it. So by the time I came to my end of my PhD, it was very clear in my mind that I wanted to go more into a teaching stream faculty position than a research stream faculty position. I liked my research, it was good, but I really loved the teaching side of it. So both of those things happened in my PhD.
Just before we touch on your thesis, I actually forgot to ask you about your favorite course in your undergraduate career.
Right. Oh, I did like a lot. It's hard to choose. Mm-hmm. So I mentioned group theory earlier, and I think group theory was very important because it helped me want to be a mathematician specifically, and not just casing courses for service of mathematics. And that was a really, really influential course, and I just really enjoyed it. A lot of people don't give this answer. I really liked my analysis course. I really liked learning about metric spaces, and I thought the sort of definitions and theorems and proofs and trying to think about the intuition, and the real numbers are super bizarre. I mean, the real numbers are absolutely nuts. They should not be considered real at all. It's a funny thing. And so I just loved playing around with some of these weird sort of examples and counter examples as happened. And even though I'm not an analyst today, that's not the type of mathematics that I went into at all. And it was nice for physics, but not, strictly necessary. It was a course I just really, really enjoyed. And so that was one of my favorite ones.
Wow.
Yeah, and for the audience and for us, can you give us like one strange property about the real numbers that we wouldn't know?
Well, I don't know whether you know it or not, but okay, so we have rational numbers like 3/7, and we have irrational numbers like pi and e and root 2 and so forth. And if you take any two rational numbers, there's a little proof that says in between two rational numbers, there's a real number. And likewise, if you take any two real numbers, there's another little proof that says in between two real numbers, there's a rational number. So when I phrase it this way, it kind of gives this like alternating sense to the real numbers. Well, there'd be a real and then a rational and then a real and a rational, and it would go on sort of this way. And most numbers you can ever name are rational, right? Like if it's not pi and e and root 2, I mean, how many other irrationals do you know? But it turns out if you were to choose and pick at randomly a real number, despite that alternating behavior that I talked about, you would get with probability 1, like 100% of the time, like always, in an appropriate sense, I'm being a little bit coy, you always get a real number. So even though between any two real numbers, there's a rational number, nevertheless, your probability of choosing a real number is 1 here. Or there's this more technical terminology about sets of measure 0, and it doesn't matter. But isn't this just bizarre? Like it doesn't make any sense.
Yeah,
but it is.
It seems very bizarre, and we're dealing with this in our calculus course right now because we're kind of relating integrals to probabilities, and then I think it's a very similar problem when we deal with, when you pick two vectors at random, what's the probability that they're linearly dependent? And it's probability 0, and you really get to see that when you learn about like Jordan measure. We're dealing with Jordan measure. I know there's another type of measuring that's better, but for now, Jordan measuring, Jordan measure is appropriate, and yeah, it's kind of a surprising result to see.
So
like, there's just zero probability.
So that's the property of generic vectors, right? Like the fact that we can pick just random vectors. I think. Wait, that's actually that's a really cool fact that I did not. Yeah, I mean, I guess we did not know that about the number system. But isn't there now? Correct me if I'm wrong, because I think I heard this somewhere, and I well, why not? I can get it checked right now. Is there something that's saying that there are more irrational numbers than rational, or some kind of crazy thing like that?
Yeah, this is basically the claim I'm making.
Yeah.
And so the standard sort of proof here is Cantor's diagonalization argument. And which is a very, if you haven't seen it, it's a very nice thing to look up. And basically it says if you go and try and list all of these real numbers and sort of enumerate them, then you're going to get something that just doesn't work. There's going to be more real numbers. So that usually compares real numbers to integers, but there's also a lovely little proof that says the number of integers and the number of rational numbers is the same. They're both what's called countable. And there's also a lovely little sort of snake diagram proof of this fact. So there's way more rational numbers than there are integers. But what we really mean by saying that there's the same number is that you can have a bijective function that goes between them. So thus every integer is associated to some rational number and vice versa. But that is not possible for the real numbers. And so for the real numbers, eliminating the rational, so the irrational numbers, there's more of them. And what we'll say is we use the word uncountably infinite for this, in comparison to countably infinite.
Yeah, because I was actually just going to say, because there is that fundamental difference, right? Because you can still have infinite but countable, and like as you just mentioned, uncountably infinite. Like that entire concept is just so interesting. Like these are
different degrees of infinity, right? Like what's going on there. And there's really deep questions about all of that hierarchy as well.
And these are exactly where I was talking about that abstraction of math, like where some infinities are like just completely different. It's not. I'm not giving the classic quote. Some are infinities are bigger than others. I'm saying some are just defined completely differently, but they're still infinity. Like that idea is just it's very foreign, and it's I don't know. It's something that you have to learn. You have to get into the groove of understanding.
You know, I think it might
it's funny
connect
that we're
to...
talking about. Oh, sorry.
No, you go ahead.
Go ahead. I was gonna say that, like when you were talking about the diagonal argument, I actually watched a Vsauce video about this like a couple of days ago.
Oh, lovely.
And when he wrote it on the like he did it by hand, and it made so much sense because I think it went something along the lines like you list like random like rational numbers, and then you can pick like each digit going along the diagonal, and it will form like a different irrational number that hasn't been listed before. And so
wow,
it just really shows cool. That even if you try to
that's really cool.
So even if you try to put it like 1-to-1, you'll always be able to construct one that hasn't been listed before. So
that's exactly and isn't that, I mean, the result is really cool, but is not the proof also a very interesting proof structure? This idea of enumerate all of our numbers and then construct a new one diagonally that does not satisfy the previous. I mean, I just love the logic of the proof as well.
Yeah, I'm just thinking about that is amazing. That is an amazing
actually
fact.
The reason why, because maybe some of the listeners didn't really catch why we're going in diagonal, but the reason is why it is because if you have like irrational numbers, they're gonna have like the position of the digit will be like, let's say the first position is a 1, second position, etc. But if you take like the first position of the first number and you use that number to construct your extra irrational number, and then while you go down diagonally, that will just automatically mean that like the number in the position that you pick will never have been put there before, because of the way you're listing all of your numbers. Did that make? I feel like that didn't totally make.
I think that would only make sense to people who've probably heard this before, or like have maybe searched this.
It was probably a bad idea.
Maybe search this of some sort.
That.
Yeah, maybe like a quick Google search might explain it a little bit better.
So Cantor's diagonalization argument is the one, and we could go and try to rephrase it, but I think you're right. It's a good one. Just quickly.
Basic idea. Yeah.
Anyways, these types of really cool little theorems just kind of blow your mind. I do think there is a sense, though, that sometimes it might connect to a little bit like what we were talking about earlier, which is when you have some of these very strange behaviors, things talking about like different types of infinity that immediately give a bit of a like blow your mind kind of sensation. It creates the idea that mathematics is very hard and sort of inaccessible, or that it would be very challenging. But a lot of these ideas actually are a lot more approachable, and you can end up understanding things like both of the subject we talked about, different types of infinity and higher dimensions. Both of those can be made a lot more understandable than your initial guess might be, because you might guess, okay, there's nothing we can really say about either of those concepts. They're both just so hard and abstract, but not really. They are really quite approachable subjects.
For sure. And for the people that are listening to us right now, we know that not everybody is like a science major, math major, or even, in university at all. And a lot of people ask us, how do you start learning math if you didn't like math in school but you're interested by the subjects? And I always tell people, go on YouTube, watch there's tons of great resources on YouTube and all that stuff, but you always have to practice. It's inevitable to practice. And recently we've gotten sponsored by brilliant.org, and they're really like an incredible resource. You can go and learn about like calculus, linear algebra, really the basic fundamental, like the fundamental ideas that you need to understand before moving on to higher level mathematics are totally accessible. And the courses over there are great because every single time you log on, you can go straight into practice, right? They teach you a concept and you practice it right away. And so, that's why I really recommend it to anyone who's really trying to like not only learn about the concepts, you can do that for free on YouTube and everything, but if you really want to learn, practice, and deepen your understanding of mathematics, I really recommend you check out brilliant.org.
Also, they have daily problems, like daily challenges that are really interesting. For example, I think I mentioned this before, but there are very logical problems that they have on there that even without going into any particular stream, you can just improve your understanding of logic. And in this episode of mathematics, one of the most important ideas in math is logic and understanding why and how these things work, just the basic fundamentals. And I think that also, it doesn't matter if you're doing really complicated stuff or bare bones basic, but logic applies in everything. And that's always an added advantage, right? So you guys can go to brilliant.org/MPP. That's the Math and Physics podcast, or just click the link in the description below. We've included it. And for the first 200 people that sign up, get 20% off your premium membership. Would you not want that 20% off? Like, it's beautiful. So anyways, go ahead, click the link in the description, and yeah. So, Dr. Bazett, I need to ask you this question now because we have come into the later stages of your academic career. So, after a quick search on your thesis, we understood that you kind of wrote on K-theory and, again, I don't really understand this, but two tuples or something like that. Anyways, the question here is maybe you would kindly, kind of dumb it down, of course, but kind of explain your thesis, because I think like the idea, I was just reading like the brief, what's that? Like your first part of your dissertation, like
abstract.
That. Yeah, like the abstract, exactly, like the abstract. And I was kind of understanding the idea, but maybe you would want to, portray it to the audience.
Absolutely.
Yeah, let's hear it.
So my thesis is really in a field called algebraic topology. And so maybe I'll say a few things about what is algebraic topology, because this thing that I specifically focus on called equivariant K-theory is just an example of an algebraic topology field. So we talked earlier about how topology was the study of spaces, but where we were allowing sort of a lot of fluidity to it. In other words, there wasn't the rigidity of lengths and angles being preserved. You can imagine everything sort of made out of Play-Doh and you can move it around. You can't tear it. You can't cut it and put it, like you have to do continuous things. And a reasonable generalization of the word continuous, as you would know from calculus. So if you're just a topologist, let's not talk about an algebraic topologist. If you're just a topologist, you're interested in studying these types of objects. And you want to make delineation. So I'll give an example. Let's imagine you take a rope and you take the rope and you tie a knot of it and then you reattach the ends of it. So what I imagine is you have some circle, but you've now also introduced a knot to it. Okay, if it's a very simple knot, I could do a knot and Parker could do a knot and Ray could do a knot, and we could glance at them if they're simple and we'll be like, no, they're different. Like this has more crossings than that one, or this one, Or it could be that our knots are the same, and if you just sort of massage them, like they're oriented in space a little differently. The exact spot on the rope where the knot is, like how tight it is, could be different. But if you massaged it, you could transform between our three knots. What do you do if the knot's extremely complicated? Like hundreds of different overlap. How would you even know whether Parker's knot was the same knot as my knot, or whether it was the same knot as Ray's, or whether they were all different? So one of the things that we want to do, that's referring more to a field called knot topology, which is a real field,
Wow.
K-N-O-T topology, not N-O-T topology. But it illustrates the idea of the type of question that somebody in topology might be interested in. And then secondly, you could imagine a similar type of thing you might be interested in. Okay, you could ask, well, how many holes does an object have? So if I look at a normal circle, a little one-dimensional circle living in, say, 2 dimensions, you could be like, it has 1 hole, and a figure 8 would have 2. Okay, we sort of understand that idea. But similarly, you could ask, well, what if it was really complicated shape, like a Klein bottle, or something even much more complicated than that? How many holes does it have? Can you use that to sort of distinguish between 2 different spaces? And the core question in topology is you have 2 different spaces, very different representations. They sort of, the way, like the formulas perhaps you've written down, or the way these spaces originated might be very different, but are they the same? So an algebraic topologist comes in knowing some tools from algebra. Okay, so algebra is, things that are, you're talking about, like, for example, the integers have algebraic operations on them. Like, you can add integers and you can multiply integers, and those properties have different types of rules to them, right? And you study all of this in the field of abstract algebra. So algebra is a very concrete field. You're talking about things like integers, or two copies of the integers, like z cross z, for example, or the rationals cross the rationals, the types of things we've been talking about. So there's a certain rigidity to it. So the idea of algebraic topology is, can you put these together? Can you, for example, find some association between a topological space and some algebraic thing? Well, I think you sort of can. So as an example to illustrate this idea, okay, imagine you're taking a loop, what we call S1, a one-dimensional circle. You're thinking, I want to continuously map this onto all sorts of different spaces. So the first thing you might map it onto is, you can imagine, I can take the one-dimensional circle, and let's see if I can do this all in audio and make it all make sense in audio. Take a one-dimensional circle, and I want to map that one-dimensional circle onto a two-dimensional sphere, so like the surface of the Earth. So this is like me taking a pen and drawing like the version of a circle, but it would be on the surface of the Earth. Now, to a topologist, because there's no, if I'm walking around the surface of the Earth, I don't see any holes. Okay, maybe there's a hole that is the inside of the Earth, but that's sort of a different dimension level of analysis. If I'm walking around the surface of the Earth, I don't see any holes. And so I can imagine, if I take my little loop, I could shrink it up to a point. And because there's no holes there, and I'm allowed to sort of stretch things and shrink things in the field of topology, it's all very, very weird. I could imagine shrinking it to a point. Does that make sense?
Yeah.
Okay.
I could see that.
Raise by me for now. Okay, so now let's imagine we're on the surface of a donut. Okay. So, and I'm trying to figure out what's going on. And what I really mean here is the two-dimensional surface of the donut. Okay. So I could talk about, for example, there's the central hole of the donut, like where the Timbit got taken out if you're in Canada. I know what that reference refers to. And then there's also like the center of the donut, because I'm only imagining its two-dimensional shell. Okay. So now let me take my pen and I'll draw another circle around that central hole of it. Well, I can't close that circle up, can I? Can't close it up in the same way I could close up the circle that was on the sphere. I can't imagine shrinking it, because it has to stay on the surface of your donut. So how can you shrink it? Because there's a hole there, it can't get around the hole. And in fact, there's another hole, which is, if you imagine going around, like if you take a bite out of it, of the donut, so not the central hole, but the fact that the surface has sort of a volume inside. And if you go around that volume, likewise, you could draw that little loop around it. It would look a little bit like a ring, and you can't collapse that one either. It's not like in the sphere where if you draw the equator, you just move everything up to the North Pole and then it vanishes. So if I said that the donut is a little bit like the integers crossed the integers, there's sort of an association there that makes sense, because I could go around the central hole n number of times, or in reverse n number of times. That's kind of like one integer, one sort of type of it. And I could go around the holes around the edges of it. And so there's sort of, when I try to think about all the different ways that I could map a circle into a torus, somehow, and I have to be precise about this, but somehow the answer of the integers cross the integers is a sort of a reasonable algebraic object to associate to this. And I mean, if you imagine two donuts smashed together, for example, maybe you'd be like the integers cross the integers cross the integers, and that would be different. And you'd be like, okay, they're different this way. So
but is it illegal to just draw the circle like on the side of, like if you have a torus, you just draw the circle like
so if we drew it on the side,
is that not allowed?
You can draw it and it would collapse to zero in the same way it would collapse to zero in the sphere.
On the sphere, right? Because it would have to be in the center for it to not be able to.
That's right.
Wait, real quick though, this might, I don't know, this kind of like backtracking a little bit, because I was just thinking about this and I thought maybe it would make sense as the explanation continued, but I was just wondering I don't know if this is really stupid, but I do have to ask this because I don't want to get more confused in case I'm understanding this wrong. You said circle, And then you said one dimension. Is a circle not two-dimensional?
A terminology point. You're quite right. So let's define something more precisely. Let's talk about S1, which I will call the one-dimensional sphere. Colloquially, we call that a circle. When we say the word circle, we think about one dimensions, but I'll call it S1 for the one-dimensional sphere. One representation of this in the Cartesian plane is all the points that solve x squared plus y squared equal to 1.
Yeah, so that isn't that two dimensions right there though? X
I see your point. Yes,
like,
it depends on.
That's what I'm not understanding. How can you call
right.
this a one-dimensional object?
Mm-hmm. So it's the difference between the object itself and the space in which that object is living. So if I imagine I'm an ant on the circle x squared plus y squared equal to 1, well, I can only go in one direction. I can go counterclockwise or I can go clockwise.
Oh, okay.
So from the perspective of the ant, it's one-dimensional. It is intrinsic to the sphere, it's one-dimensional. You're completely correct. This is the way I chose to represent it was embedded in the 2 dimensions in a specific, coordinate system. Mm-hmm. That's obviously not the only way you can talk about a circle. So in the same way, okay, what's S2? In Cartesian, x squared plus y squared plus z squared equal to 1. It's a 2-dimensional surface, because like if we think of living on the surface of the earth, we're like, I can go north and south or east and west, 2 dimensions. But of course we live in 3 dimensions.
Okay.
So I can talk about the n-dimensional sphere as well.
Mm-hmm.
So this is the context in which I'm sort of describing this problem.
And was there anything specific that, because again, we don't truly understand them. I mean, you truly helped us understand the idea behind it, but again, I don't think I can say I understand K theory. So I guess
I haven't even told you what K theory is.
Yeah, exactly. I was just gonna ask. So like, is there any like realization, any kind of what am I trying to say? Like any kind of result that you saw from your thesis that That's maybe right. You can
So now that I've given this very brief introduction to the idea of algebraic topology, the way you associate specific algebraic structures to specific topological spaces, I mean, then there's a question of, well, what was the specific topological spaces I was interested in my PhD thesis, and what was the specific algebraic structure that you were associated to that? So I'm going to introduce just one piece of more sort of technical terminology, and then I'll just speak in generality. It's the idea of something called a vector bundle. The vector bundles are really interesting objects. So the idea is, imagine you take your circle, your one-dimensional circle once again. I want to imagine at each point on that circle, I'm going to associate, how about a vector space? What am I even talking about? So I'll give you a concrete example would be a cylinder. A way I can think about a cylinder is there's a circle on the bottom, and then at each point on the circle, I associate a copy of the real numbers, an R, and that would create this infinite cylinder. Or I could associate perhaps just the interval 0 to 1, and that would give a little cylinder of height 1. So that's a very concrete object we understand. And the idea is I associated the vector space R, it's a one-dimensional vector space, to this underlying object, which was the sphere. This circle. At every point on the circle, we associated to it this line. Okay, well, I'll give you a different vector space. It's the Mobius strip. So the Mobius strip is like a cylinder, but with a twist in it, right? So the Mobius strip still has the property that you start with a circle, and at every point you assign a little line segment, but somehow the way it's glued together globally is different. So that is a different vector bundle than the cylinder vector bundle. So K-theory effectively is a field of algebraic topology that analyzes and associates to vector bundles like these. And it looks at a space and it says, what are all the vector bundles on the space? Makes an algebraic structure where you can add and you can multiply those vector bundles over the space. It can be infinite dimensional. You can add a group action that spins everything around. That makes it equivariant. There's all sorts of fun things you can do with it.
I am mathematically not allowed to comment on that.
So let me say the thing that's in generality now. So the spaces that I was interested in is a field called symplectic geometry. And I'm not actually a symplectic geometer. This is not my specialty, although I tangentially come into it. But symplectic geometry for you two is relevant from physics, because both classical mechanics and string theory can be described in the language of symplectic geometry. Symplectic geometry allows many different types of things, a sort of a version of calculus you can do, for example. And so it was actually for the purpose of understanding physics that the types of spaces ended up originating. This field of symplectic geometry came up to answer these problems in string theory and classical mechanics. It's really nice that it does associate to both of those. And there's still words like energy and momentum that float around in the language of symplectic geometry because they still have this sort of historical connection back to physics. But symplectic geometry is now a mathematical field in its own right. So people prove theorems and deduce results and are interested in results in symplectic geometry separate from, do they just help us understand our physics? And so really what my field was to use algebraic topology, this way of associating algebraic structures to topological structures, to very specific questions within symplectic geometry, specific spaces that are originated. You try to understand them and you will compute out the so-called equivariant K-theory of these things. And that's the idea.
Wow. So, wow. Yeah, really, wow. So that's okay. I think I kind of understand the picture that you were painting. But again, like I wouldn't really, I mean, not that we're expected to like solve a problem in this field, but like I think I kind of understand.
Don't quiz me on it.
Yeah, exactly. Like where you're going with it.
The test is next week on Monday.
So I guess now that you've explained this relatively difficult topic, I guess it's a natural question to ask you, has there ever been, or what is the most complicated topic? Because as you obviously mentioned, you're a YouTuber, you teach on YouTube, you're a teaching professor in your university. So I guess, what is the most difficult concept, much like this one, that you have ever had to teach? That you've and what was the experience with the students learning that concept? Like, were they accepting it? Were they finding it really hard? Like, what was your experience in that regard?
That's a really good point. I think the hardest topic, it's actually very interesting. On my YouTube channel, I posted a video on Bayes' theorem. And Bayes' theorem is actually, for whatever reason, the most popular video on my channel. I think it just gets searched a lot. I think it's picked up not from algorithmically, it's picked up by search. So a lot of people search for it. And Bayes' theorem is a really interesting because there's a formula associated to it, but there's also a real shift in perspective. So this is a theorem in probability, and we're talking about if you learn new information about the world, how do you update your probabilities that other events will happen? How do you incorporate that new information? And so there's a real change in perspective from when you're thinking about the world as like, this event happens or that event happens, versus there's a series of probabilities by which I'm confident that things will happen. And as I learn more and time goes on, I update my probabilistic view of the world. And I really wish I could go back and replace my exact Bayes' theorem video with a new Bayes' theorem video, and that one would have all of the views, because it really leads to a lot of confusion. It led to a lot of confusions in my own classrooms and YouTube as well. It just has tons and tons of questions, and students who have to take Bayes' theorem in all their stats courses and all their probability courses all around the world. So it's a classic of it. I think it can be done well, but it's still nevertheless hard to teach. So I think that's my answer. Either that or strong induction. I don't know. No one gets strong induction.
Interesting, because so I'm actually. I mean, I think the audience. I mean, you guys should know this, but like I'm in a statistics major, right, at the university. So I do understand where Bayes' theorem could be a little, because Bayes' theorem is the conditional probability theorem, correct?
That's
right.
Yeah.
So it's dealing. I guess I could understand where it would be confusing, but is that the hardest conceptual wise that you have ever taught? Because I'm trying to ask, because I'm thinking about conditional probability, and I guess I can imagine the concept, but I was just wondering if there would be just a concept that no one really gets, because there are some, especially in, for example, giving the physics example, like in quantum mechanics, right? You can list out the whole course as very hard concepts, right? So I guess I was wondering if there would be any conceptual difficulties like that you might have encountered along the road.
Yeah, I see your point. Yeah, because I'm sort of answered it first relative to a specific audience. Like, this is a topic that is for the audience of which I teach it is often very challenging.
Okay.
But someone who's a stats major and has doesn't have that philosophical, already has that philosophical shift in perspective, doesn't find that particularly challenging. So I teach a modeling course. And this is also not going to give you the answer that you want, but you're going to have to deal with it nevertheless.
Completely okay. I'm okay with it.
I teach a mathematical modeling course.
Okay.
I know it seems weird. I've gone full circle and I'm back into applied math after my foray into pure math. And what's different in a modeling course is that a lot of the approaches that you take have a different sort of spirit to them than when you're in a course where you're like, I'm going to learn how to do differential equations and I'll solve this type of differential equation or whatever. Because you're doing things like questioning the validity of the assumptions that you're making and trying to assess whether or not a mathematical model that you have has strengths and weaknesses. That is, you're adding qualitative things and not sort of quantitative. That's not quite the word for it, but you're not adding things which is just like you apply the methodology, you can prove the methodology works, and now you've gotten to this result. So this is a subject which I'm as I said, I'm teaching it right now, and I find extremely easy to say and extremely hard to really meaningfully understand what we're talking about here. Like, how do you actually develop those types of abilities? So I do my best I can, but that even for third year students, I think is definitely very challenging.
Yeah, that was actually like that was my exact question.
Okay.
about like the hardest concept that you've had to teach. So that was perfect.
Even though it's not like a deep, mathematical concept like Jordan canonical form.
Yeah, exactly. It's just something that's hard for people to understand. So yeah, I just wanted to know. So that's interesting. That's interesting. Yeah, Parker.
So for your modeling course, is there an example of like a concrete question that you would ask in that course?
Oh, absolutely not. As in, I try not to ask concrete questions in this course.
Oh,
okay.
So, I mean, as in, I try to make the students ask concrete questions. So we might say something quite vague, like, how do we model a pandemic, for example? And this is obviously a topical question. And even when you phrase it vaguely, you can start answering it in all sorts of different ways. Are you going to try to do some sort of statistical model? Are you going to do some system of differential equations? Are you going to do some sort of cellular automata thing? Like, there's all these completely different fields of mathematics that might come and be relevant to that problem. And then even if you lock in one of those things, you could try to say, well, one second. So what are the interesting things we're trying to accomplish when we model a pandemic? And so it's sort of like the part of the modeling process is narrowing down to that well-defined problem that when you've almost defined it precisely enough, then you can write down the mathematics and get the conclusions that you need. So the beginning is actually often quite vague.
So it all depends on your goal, essentially, what you're actually trying to do, and then the method kind of follows from there.
That's the spirit of it, at least. It doesn't always work out quite so cleanly that way, but that's the spirit of it.
So as having graduated, or at least with with a PhD in a mathematics field, even though we've had like mathematicians on this podcast, I've never really asked this question.
Okay.
And I've always wondered, and I guess today's the lucky day. So I'm just wondering, before you actually got your PhD, what were your, I guess you already kind of told us, but like, what were your career goals, like, to do with mathematics? And like, just forget the teaching part for now, because we obviously know that's what you're in right now. But just like in the field of math, what would be a typical mathematician's goals?
So, I mean, it really depends on, I think that people go into graduate school and come out of graduate school with sometimes different things.
Okay.
So say you're doing, and I think honestly this conversation I'll answer for math, but I don't think it's necessarily all that different if you're doing a physics PhD as well. So one goal that you might have is to be a research professor. And I think I might have had this goal to a degree, but maybe wasn't actively thinking about it all that much. And so really what that would mean is that you were wanting to be able to, you were enjoying the research you were doing in your PhD, and you wanted to be able to continue having a space where you were doing pure research, you were collaborating, you were going and speaking at conferences, publishing papers, having graduate students, and you wanted to go on and get a faculty position in a research mathematics. So that's one career path that people could take. And another career path they could take, and in mathematics this is not uncommon, is you say, I have a math PhD. This is a proof that I am sort of quantitatively literate and intelligent at some level. I can tie my shoes, and I'm going to leave mathematics a specific field, but I'm going to be, who knows, some sort of data modeling for TELUS. I don't know what it could be, right? The point is you go off and be and work in the industry. Now, to me, I had always liked academia and was more under the impression that I would go after my PhD and maybe do a postdoc and be on the track to try to eventually get a tenure track position. It just became clear to me that I really wanted to get that to be a tenure track teaching position and not a research position as time went on. And in many ways, these things just sort of level up. What is a postdoc? Well, a postdoc's kind of like doing a PhD. Maybe the expectations have changed and the timelines have changed and the supports have changed, but it's sort of the same.
Wait, they're different things? Wait. A postdoc and a PhD are different? I thought that's the same thing.
Yeah.
No, they're a different step. So after you got a PhD, if you wanted to continue in academia,
postdoc is after PhD.
After PhD.
Oh my, so PhD isn't even like the last frontier, like there's more.
Oh, that's the bottom of the ladder. Come on now.
What? That's crazy.
I get a little bit. It's in the middle. So most people would not say you got a PhD from the University of Toronto. The chances are you would not be hired at the University of Toronto as a professor the next year. That'd be very, very rare.
Okay.
I actually weirdly had a 1-year contract as a professor right after that sounds weird, but that's only because it was a teaching position. And sort of, it was called a professor, but in many ways it was sort of analogous to what most people do with this postdoc, which is a temporary position at a different university for the most part, where you go off after your PhD, you're working with new people, and you're sort of like continuing the projects of your PhD, as well as starting to work on new things with these new collaborators at this new university, and trying to think more broadly about what would a 5 or 10-year research program look like? And it's that program that I will use after I've gone through 1 or 2 postdocs to apply for the tenure track position. Wow. Maybe if you're exceptional, you can skip this, but that's the standard.
Oh wow! So they're just very different things. Okay. Well,
and they are different. I mean, you'd be paid more, for example, as a postdoc than a graduate student by a large amount, and less by a large amount than if you were a professor. So it's sort of it's a very sort of middle ground type of position.
So postdoc would be, so is postdoc the last step, or is there something even more than that?
Yeah, a postdoc, and then you would probably, if you were going in the standard track, then you would apply to be an assistant professor.
So this is all obviously in the track of academics, right?
Exactly.
This is all in the track of academics. So
right.
So I guess a natural other question would be, did you have, so I guess as you already mentioned, you were always intrigued with academics, but if you had to describe your ideal job before you got into the academics field, like frame of mind, if you had to describe an ideal job in the field of mathematics, what would that be for you? This is very obviously subjective.
I don't know. I say my current job is kind of ideal right now.
Well, that's perfect.
I feel very lucky. The reason I say this is that, so one of the beliefs that I have is that universities should have very high quality teaching positions. So what I mean by high quality is, for example, it's tenure track, so you can go on and get tenure, and that they're held at sort of an equal level of respect and responsibility to any research professor that you would have as well. The difference would just be that the ratio would be shift. You'd be doing, so in my case, my responsibility is 70% of my time is focused on teaching, and 10% of time is focused on scholarship and 20% on service, whereas it would be a bit more equal if you were in a research stream. So my belief is this is a very, very valuable type of position because it lets people try and really focus to be the best professors they can for the primarily undergraduate students, but sometimes graduate students as well. And there's been a movement over the course of the last 10 years to start accepting this. And a lot of the big Canadian universities and in the United States have started to increase the number of what I'll call high quality teaching jobs. This is in contrast to what are sometimes called sessional positions or lecturer positions, which are often temporary, underpaid, not a long-term contract, all of those types of things. So it's important to have this sort of high quality thing, and you attract, in theory, high quality people that do a good job. So they're rare. Only a couple in Canada become available in a couple of years. And so I applied to a good number of these. And I think the University of Victoria's one is pretty much ideal at really respecting and valuing teaching, putting it into a good position, having a bit of scholarship, all of that kind of stuff. Now, I probably wouldn't have given that answer, which I think is where you're kind of going with it, if I was finishing my undergrad. But honestly, I wouldn't think about it all that much. I mean, this might seem silly, but getting a PhD was kind of the path of least resistance, in the sense of like, what else was I going to do? Get a real job? That's not like I just been doing math and physics for 4 years. And so there wasn't like, I'm going to go and be a banker motivation. And so it was like, well, I like what I'm doing. I'm doing well at what I'm doing. I'm going to continue doing it. And so, I don't think I really started thinking about the future until halfway through my PhD or something like that.
So,
oh, wow.
Apart from academics, is there like again, this is like not to seem, like, this is just a very general question because I'm just inquisitive. Fine. Like, is there a path that you can take not relating to academics that is still like with your mathematics degree? Because like, as we were talking about, like in higher levels of mathematics, it does become, extremely abstract and it's all just in your head. So I would assume that all of that is relating to academics. Like, you would be able to use it in an academic field. Where would that be applicable in, like, I don't know, like another job or something like that, like apart from academics?
A lot of people do go into industry and they take their skills. And we should also recognize a lot of math is not pure math. A lot of math is applied math. A lot of math is statistics. A lot of math connects to data science and many other different fields. But even if you had gone in and you've done if I had taken my PhD, okay, I can't actually imagine a job that I could use the actual like subject matter of my PhD in. But I think there's plenty of jobs where you could take the analytic skills and make a case that they should hire you, and they do. So a great example is there, I don't know if you know this, you remember in 2008, there was a bubble in the American housing market that caused a big problem for the whole world, right?
Yeah.
Yeah.
Well, there was also another bubble. I'll claim it's equally important. There was a bubble in Bay Street and Wall Street hiring PhD mathematicians. Because it used to be that there was a large number of sort of people that would go, and it still is today, but there just happened to be a little bit of a dip for a little bit there. A sort of quantitative analysis. You try to hire the best and the brightest, and you're going to go and be working on all these weird pricing models and blah, 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 blah. And rather infamously, one of these models was sort of misinterpreted by the banks and went quite badly in 2008. Anyway, so this is just an example of a lot of people could go off and do that. And I know several colleagues who got a PhD in math, and they're just working in industry, and all their jobs are all different, but they all sort of make sense that you'd be like, oh yeah, someone with a math PhD would do great in this particular job.
Wow. Okay.
Maybe one other thought on the same idea is I can share that my brother is in human genetics, and now he works for a biotech company. So it's not math. But he, after his PhD, did do a postdoc, but not an academic postdoc, an industry-based postdoc. And then he never left industry.
So that also works. You can even do an industry postdoc. That's interesting.
Right. Often they go back, and maybe there's some crosstalk with the supervisors, but that's a possibility as well.
That's interesting. That's very interesting.
That's going to be very common in physics, I would guess.
Mm-hmm. Mm-hmm. Yeah, I think maybe more common than like mathematics, because physics is like directly applicable in the physical world.
Absolutely, yeah. I mean, there's also things you'd be doing, I don't know, some bioengineering, little sensor company or whatever, and then you would do it there, and then maybe you like the physics that you were doing there, or maybe you didn't. For sure. Yeah, I mean, we have a lot to think about, of course.
We are below the bottom step on the ladder still.
Oh yeah, we're still like.
No, you guys are doing great. You're exactly where you should be. It's perfect.
I mean, yeah. So like, we're still in like second year of university, and we think this is it. This is the 4 big years. But then like, yeah, another 4 big years coming ahead of us, and then another 4 years after that. It's but I guess that's the journey, right? That's the whole journey. Like appreciating the fact that we're doing this, and living through the journey is what's exciting. Especially in fields like this where
Absolutely.
the academics and the journey is what's interesting, right?
I really always encourage undergraduates because so for example, myself, I'm just more solidified, right? It's not that I can't change my stripes at this point. I could, but I am very solidified because of just being, let's say 1 decade further along. But when you're an undergraduate, you just get to really explore and see what is it that you're actually interested. Like, do you even want to go to graduate school? Maybe, maybe not. I mean, it doesn't really matter. And so if you find that you're loving a direction and you keep going on it, I mean, yes, it might sound like there's a lot of steps ahead of you. And I guess there are. Like in a couple of years, I have to try to get promoted for associate professor. So I still have to be doing a good job, and I'm still evaluated, and people give me not quite grades, but more or less people still give me grades, and they will when I go up for full professor. Like it's a long journey, but I don't think that's unique to academia. Like if you say I'm going to go and work for Google, yeah, it's a long journey in your career at Google as well, right? So
it's all dependent. Yeah.
I'm not really thinking about that stuff at the moment, though. I mean, I've thought about it, but it's like I could change my mind at any point still.
Yeah, because we have like our entire future ahead of us.
Exactly.
Like
I mean, you've got lots of time to be taken to the dark side, as I put it earlier, and become algebraic topologist. Right?
I love how you say dark side when we're talking about mathematics.
Is physics the dark side, perhaps?
Oh no, I don't think. Oh, that's a tough question. There's no way.
Yeah. Just bringing it back a little bit more to the math world. Yeah. I wanted to ask you if you had like a math idol. Or someone you look up to in the math world, or maybe like a mathematician that has like your favorite theorem. You came up with your favorite theorem, something like that.
Well, I'm definitely very motivated right now by probably the 2 biggest YouTube channels, like 3 Blue 1 Brown and Numberphile, and I think that because I have this weird dual role where I'm teaching, but I'm also trying to do sort of global outreach through the YouTube channel. I really have tried to focus on how to be crafting really effective and beautiful mathematical stories, right? The type of thing that you would watch in theory, that if you did it well, right? Someone like 3 Blue 1 Brown does it beautifully. Mm-hmm. You would watch and you would have not just an increase in your knowledge, that's sort of tangential, but an increase in your like inspiration and like sort of motivation and sense of appreciation for the concept of the topic or whatever's being discussed.
Right.
And I find there's a weird duality between like YouTube and my own class. Like I teach classes with 250 people in them, and it's a big lecture theater, just the same way I'm sure your classes are as well. And it's a very different experience standing for an hour and a half there and giving a lecture at a chalk talk to recording a 5 or 10 minute green screen video, right? They've seen different things. But I feel like by focusing on the videos, and I've learned so much, and from those 2 channels in particular, about that sort of narrative element to math pedagogy, that now I try to bring it back in, and I've really changed a lot of my perspective. So I love that part of it.
Also, like when you're teaching a class, like you're teaching a group of 200, 300, 400 students, let's say 500 at max, let's say, but on YouTube, your audience is in the tens of thousands of people. Tens of thousands, if not hundreds, and if some like 3 Blue 1 Brown, you see millions of viewers seeing videos on mathematics. So the audience, like the fact that you're saying like, focus on YouTube and stuff, like makes total sense, because like the reach that you can get from your YouTube is just vastly different, vastly greater than any possible thing you can get in class.
Yeah, it's broad but shallow though. So where I'm at right now, I get about like on a good day like 20,000 views a day, say. And you're right, that's more students than I'm going to teach maybe in my career.
Yeah.
But when I have a student in my classroom, we can spend 40 hours in the class and office hours, and I'm taking them through all the materials for them to study and do well. And it's this really deep and intimate experience. So I can imagine them be like, well, I really changed. I mean, this is the hope, right?
True.
That I would inspire someone for a long time. Now, if you go and watch my Bayes theorem video, because you type in Bayes theorem and then you watch it for 3 minutes and click away, okay, you contribute to the 20,000 views thing. Yeah. But to what degree is that a deep change in mathematics? Now, right. I think the big people like you're talking with 3 Blue 1 Brown, they do really start to shift people's perspectives over the long term. And I just haven't been able to because I'm mainly focusing on my own courses, right? So I think that they do get that in the long term, or something like with your professor, if they're assigning my videos all the time and now you watch a dozen of them or whatever, then the way my emphases and the way I think about things might start to creep into your mind and make a real change. So I like YouTube. I like its potential, but I'm also not 100% like set on it. Yeah, I don't know.
Yeah, I totally understand how like personalizing like with a student, like, because especially like, I mean, if anyone's ever tutored here before, so they're like the most common, like if you've ever done that in high school or anyone, like, that experience of helping someone, because I guess on YouTube, you're very right. Like the real people that you're talking to, or I guess seeing, are just the people that comment, like, okay, they leave one line, they like, subscribe, good stuff. But when you're teaching a person, it's active back and forth that I totally understand you don't see on a platform like YouTube. And I mean, that's not the purpose of it, but that's just a different perspective. That's just a different shift. Yeah, I understand that.
I remember a little while ago, I got a comment on my channel and the person said, so hilarious. They said, thank you so much. I watched your entire playlist of 84 videos this weekend, and I think I'm going to do well on my test tomorrow. And I was thinking, you watched 84 videos what did you learn? Did you get negative value out of going through this experience? So it shows that relationship where, I mean, I'm a believer in my classrooms of people being actively engaged in doing mathematics, right? That, like, as you know, if we didn't have any homeworks and you just sat there and just copied everything your professor said, how much are you really going to learn? It's very important that you're actively engaged in your own learning. Probably more important than listening to me ever is going to be. But YouTube is a very one-directional, very passive kind of experience. And so I try to do the best I can, but it is like intrinsically a not ideal experience despite its massive and powerful reach. So there's this tension between it. I don't know.
Yeah, very true. Like it's practically impossible to like learn everything and retain it just from watching YouTube videos. It's so crucial to like if I teach you how to graph a line, you can't just absorb it and say, okay, now I know how to do that, let's move on. You have to actually practice, and it's a shame that I think some people kind of miss that aspect of their learning. What would you call that?
Like their journey, like they're missing out on the practicing portion. And I think this is very, very applicable in the field of math, especially because Absolutely. I think mathematics is the one field where without practice you are seriously doomed. Like, I guess, like, there are still especially, like, okay, I'm not going to hate on anyone here, but, like, especially in biology, for example, like, it's, like, for your tests and everything, it's, okay, can you remember this graph? You can remember this paragraph. Okay, spit it out on the exam. But, like, in math, there is nothing like that. Absolutely nothing. Like, without truly doing it yourself and understanding how to use your information from this one problem and apply it to several with the same idea, if you can do that, that is when you truly know or understand the concept. So that's right. The difference between understanding and knowing is very prominent, I believe, in the field of math. And you truly get to know it in math. That's the one field where you see it.
I also find that there's sort of a version of rote memorization in mathematics. It's not quite the same like it is in first year biology, but it's there's a difference between gaining procedural fluency at some type of computation. So if you're doing multivariable calculus, have you guys done double integrals yet, for example?
Yes. Yeah.
Right? So there's sort of a procedure there that you do, and you sort of set them up in the same way, and you visualize it, and you can get very good at the procedural fluency aspect of it and execute things and get an A in the course even sometimes. Well, also really missing we're really missing like the conceptual understanding of what's going on. Like, I know I use the formula that has the Jacobian in it, but I don't, it's just there. It's a thing you compute. It's a determinant. I know if this happens, I plug that in. That's fine. And so I think a lot of students in second year get into a little bit of a trap where they are slightly focused on, okay, I've got these sets of problems and I need to do exactly what you said, which is I figured out how to do this problem, and then I'm going to translate that knowledge to similar problems that are like a little bit different on the test. Let's put it that way. But any time that you sit there and spend thinking, saying, why is this true? How does this generalize? What's a special case of this? Why is this different than another thing? What's the connection between these two things that are sort of similar, but any time you're spending asking yourself questions like that over, okay, this is the method by how I apply L'Hopital's rule. I take the derivative on the top and the bottom. You know what I mean? Like that procedural fluency stuff. The more you focus on the sort of developing sort of a conceptual understanding, the better you're going to be in the long run.
At least that's why I appreciate the math stream that Rayhan and I are in right now, because at U of T there are 3 streams. There's the 3.5, the 3.7, and the 5.7 stream. Yeah. And the one that
you're in the 3.7 stream.
Yeah, the 3.7, where we see like the computational side and the proof side. Yeah. And I feel like in the 3.5 stream, where it's purely computational, you really do skip over the why of what's happening. You just learn, you know, how do you compute the integral? Here are integrals for you to compute. And
I actually have a friend, so like in another course of mine that I'm like talking to, and he's in the 3.5 stream, and man, this guy, he doesn't understand why he is doing half the things he's doing. Like, you know, like especially with us, like when we're given solve this integral. Oh, you cannot solve this integral. You must check, is it integrable? Is this true? Is this true? You got to check the assumptions. You got to go by. So you're basically understanding, well, is this question even valid? Can I even ask this question? And that idea is something they just skip over and completely forget in the computational stream. And I think that's with all computational streams in mathematics, that they don't really go over the reasons, the rigor of why some of these things work. Now, obviously, the higher level, the 5.7 stream, which is the analysis, right? That's the analysis stream? Like, that's what it's called, right?
More that direction, yeah.
Right, so that's more the analysis stream. That would be... Wait, have you taken that? Like, would you know anything about that course, by the way? The analysis stream of math?
Yeah, so I'm vaguely familiar between the 3.5 and the 3.7 and the 5.7 stream. I always taught the 3.7 stream for whatever reason, which is the same one as you guys. But the 5.7 stream, I know basically the idea of it. They try to be a little bit more like proper analysis level rigor applied to the subject matter.
I mean, I've heard it's pretty daunting, because I've heard that they basically take any complicated word that you can think of and they put it in that course. like that's how our professor explained it. Like, if you want to take 257, it's everything you learned in this plus any word in mathematics that you can't understand. It's in that course.
That's right. So you do, for example, like epsilon delta proofs in your course. Is that right?
Yeah.
Okay. Yeah. Because then that which is a way to think about this, is that this is a more rigorous and appropriate mathematical definition of the concept of the limit. If you don't use the word epsilon and delta, you're left with the equivalent of, well, as this thing gets close to that thing, then this function gets close to this L. True. And what do you mean by close? I don't know, right? True. So you can upgrade this notion to epsilon delta, and what that really gains is there's a kind of a suspension of disbelief that happens with limits when you don't know that definition. And the same is sort of true. So I don't think calculus, it's not necessarily the case in my mind that there's a clear hierarchy there, that taking an analysis view, for example, is just like superior and you learn it deeper than a non-analysis view of it. For example, I teach vector calculus these days, not from an analysis perspective. We don't use the proper terminology of differential forms. I sort of lie to my students. They have a bit of a suspension of disbelief. I mean, I tell them when I'm lying to them, so at least they know that, but you get the idea. But in vector calculus, you learn all the incredibly important things that you need for physics to understand what E and M is and all the other things, right? Stokes' theorem and divergence theorem and line integrals and surface integrals, these are buzzwords, but all these things you'll do a ton of in physics. And so I think you can very deeply understand the conceptual relationships between the formulas and the major theorems and what they're trying to say. And that's one direction you can go, even if that is different from a direction that treats it with more mathematical rigor. So it's not always the case that going up in mathematical rigor is like, I have a better conceptual understanding. Yes, that's sort of the direct, broad direction of the arrow. But the point of trying to deeply understand why something's true, even at the level that you're at, is still very valid, at least in my view.
For sure. Yeah, I totally agree. And you know how, like earlier I was saying, like that in the 3-5 stream where all they do is computations, sometimes depending on what you're going to do in the future, that's totally fine. And there's absolutely nothing wrong with that. I'm just saying, like, if you really want something more from math than just the result, then it's definitely recommended to like go a little bit deeper, try to understand what's actually happening,
because the computational stream will only allow you to, it's basically for people who are like, I'm not going to need mathematics in my future. But right. if you ask yourself the question, would I need math, and obviously if you're in a physics stream, then the answer is yes. So if you ever have that question, then I think this the proof stream, or the middle stream that we're talking about at least, is a fantastic way to go. And I think all universities have this difference in like a computational stream of mathematics and like a rigorous stream of mathematics. So I mean, if you guys are in university, definitely like check out, at least look at the rigorous stream and see if you guys would, like it, prefer it, or stuff like that. Yeah, I can see it.
Sure. I slightly forgot it. I think U of T has a way to change streams as time goes on. Is there not some sort of, there's sort of like an upgrade type course or something like this? I've forgotten the details.
I think it's a downgrade option, to be honest.
Yeah, I don't think it's an upgrade.
Like,
I don't think it's an upgrade option.
Like if you start in like 257, I think you have a month to downgrade for free, like with no consequences.
I think the same thing applies with 157, and they only do this for the 57s. Like they give you like an extra period of time to downgrade because of the whole situation that is really hard.
I guess my question is, if you wanted to take 257, you probably have to go back and take 157.
I'm not entirely sure.
I know
I have one friend who took 237 and the year after took 257.
Oh yeah, okay.
So I don't know. Maybe
I would like there be a way that could happen. That would make me feel good.
Yeah, for sure. Because I do think it would maybe be a little bit more complicated if you did have to go back and take 157. Like technically it's a first year course, so then you'd have to like go back in your not your level, because it is stepping up, but you'd be taking courses alongside with other first years while you're in third year. So I don't know.
It's also worth saying that U of T is an enormous and prestigious university. And so they are slightly more streamed than some other universities will be. So for example, University of Victoria, which is a great university, but it's a little smaller, we don't have quite as many streams just because it's not really possible. So analysis for us doesn't come into a second year course. And then you typically would have taken a course like the ones you're describing about, but then you sort of get this addition on top of it. So there's different strategies at different universities to how you might want to do it. And honestly, my only advice to somebody who's just sort of broadly thinking about this is to, at some point, expose yourself to a more rigorous proof-based course, just to see whether you like it, just to give yourself that experience. Like that was me, and it happened to be in algebra and group theory, not in analysis, but whatever. Having that exposure to that course, as we were joking earlier, was what really started, this transition.
So to get into the analysis course after a quick search, not only do you need 157, which is your first year analysis, but you also need the harder variant of linear algebra, which is your 247. So you kind of need, so again, these codes that I just gave are very specific to the University of Toronto, but basically, at least, I mean, I'm assuming the idea is similar for all universities. Like if you want to go, like the higher analysis courses will require some lower analysis course plus maybe some kind of linear algebra as well. So it's
And
some kind
that
of
does
combination.
make good sense.
Sorry?
Does make good
There are
sense.
always
Yeah, it does.
ways around that, though. I think that like the prerequisites are always like recommendations, but if you get like a signature from somebody, they'll let you in the course.
Really? You can
anyways.
just skip the prereq?
Yeah.
That's interesting.
Yeah, you can. It's
If
just
you've
a
got good reason for it,
recommendation.
that's at least how it normally would work, right? So if someone
Mhm.
came in and I had sufficient reason to believe they had the mathematical strength to make a jump between different streams. Well, there's someone. It isn't me, but there's somebody that we would send the person to go talk to about this. And because you do want to have a bit of flexibility here, and it is somewhat unfortunate if you find out later you would have rather been in a different stream than the one you're in, and how do you make it happen?
Yeah.
So sometimes you can get around these things, but the exact procedures will differ university to university.
For sure,
that's
for
true.
sure. So yeah, we are coming up on an hour and a half now.
Oh,
This is
goodness.
officially the longest episode of the podcast that we've ever recorded.
To be honest, though, I think I should say that I think we're going to start like not keep a rigid. I mean, not that we ever did keep a rigid schedule for the podcast.
We don't have one.
Literally never
No.
did. But usually we were trying to keep it around an hour, and I think we can still do that for like episodes with Parker and I, because we can always make part 2, 3, 4, 5, 6. But I guess with a guest on, like, it doesn't really make sense to like restrict the time. And as long as we like get out all the major things that we want to talk about, like, I think that should be the goal. It shouldn't be the time that we're looking at. So to the audience, you might be seeing some, I don't know. I mean, I'm not saying anything like preemptively, but you might be seeing some longer episodes with the guests. And I think you should like that. Like, it's nicer because these guests are super cool. So, yeah. So obviously, once again, Dr. Bazett, thank you so much for coming on the podcast. It was great having you on.
You're absolutely most welcome. Thank you for the conversation. I enjoyed it. I'm glad it went long.
Truly
because,
was. Truly
I
was.
enjoyed the
It
conversation.
truly was. We learned some
and
very interesting mathematics today.
we'd love to have you on again, of course, sometime in the future. We do have exams coming up, but you know, sometimes after that.
All right, that sounds like a plan.
Yeah, sounds great.
So is there anything we need to mention? Follow us on Spotify, on YouTube, Apple Podcasts.
Wherever you're listening to this, just jam that follow button. Just
for sure.
jam it. No, hard as possible.
We do post the video version of the podcast on YouTube, so make sure to check that out if you are listening to the audio version.
Also, if you have seen any previous video version and you're on the audio version, you're on the audio version right now, be sure to check out the video version to see my phenomenal haircut. Something that is brand new, because I don't know. I mean, for the listeners of the podcast, or at least the viewers of the podcast, you might have noticed that I had very long hair for a very long time.
Wow.
So finally got it cut. So if you want to see my haircut,
I was going to get a haircut literally today. My wife said, "Trevor, it's too long. You need to get a haircut." And then I remember when we were doing this podcast, and so the listener should come to YouTube to experience the full visual before it's gone.
Exactly.
Awesome.
Okay, basically it.
This has been episode number 53 of the Math and Physics podcast. I'm your host, Parker.
And I'm Ray. And we will see you soon.
Bye, guys.